In this segment, we will look at mechanical system modeling and various coupling mechanisms. And we'll also make use of mechanical electrical analogy, and then we'll see an electrical model of this mechanical system, and we'll talk about different coupling mechanisms and look at four-quadrant operation of these systems and also dynamic operation. So let's start with this analogy that this is one of them, that torque can be represented by a current in the electrical circuit. Angular velocity or speed can be represented by voltage, angular displacement, theta by flux linkage, and then moment of inertia can be represented by capacitance, spring constant that I talked about, that K in the previous module is 1 over the inductance, and this damping coefficient for representing friction by 1 over resistance, and the coupling ratio by means of a transformer ratio here. So we'll make use of these things in our discussion here. So again, let's look at a very simple system where a motor is driving this load here, and motor moment of inertia and of that load are given, and let's say that this shaft is not infinitely stiff, then in that case we will have this electrical circuit where this electromechanical torque coming in is represented by a current source, the load torque by this another current source, it's in the opposite direction, and then the moment of inertia of the motor by this capacitance, the moment of inertia of load by this here, and then we have the angular speeds at two ends, omega m and omega l, which are different, and this ground is just a hypothetical reference in this circuit. And then this shaft is represented by this 1 over k. But when we have infinite shaft stiffness, in that case, when that is k is infinite over here, as you can see here, in that case, there is no difference between omega m and omega l, and we can simplify this representation and talk about an equivalent moment of inertia, which is the sum of the two moments of inertia. Okay. Let's move on to coupling mechanisms. These are required when, for example, this motor is driving a load, motor is rotary, and this load is linear, then we need to convert rotary motion to linear motion. And very often, motor prefers higher rotational speed than required by load, or here I could add prime mover and give an example of a wind turbine where the blades are turning at a much slower speed compared to the motor. I'm sorry, compared to the generator, so we need a gearbox in the middle. And similarly, if the axis of rotation needs to be changed, then we also need a coupling mechanism. So there are various types of coupling mechanisms that we'll see. One is this conveyor belt, also called belt and pulley. We have this rack and pinion, or a lead screw type arrangement, or gear mechanisms, which are most common. So let's start with this. This arrangement here, where we want to convert. We have a linear motion that we require, but we have a rotary drive over here, rotary motor here. So this mass is to be accelerated. So the force that is needed is mass times the acceleration, but it's being opposed by the load force, so we have to add this term over here. So that's the force that we need to produce, and the The angular speed is the radius of this pulley times the rotational speed omega m. And so if you multiply this side by r, which is the radius of this pulley, and and then make use of this u equal to r omega m, the torque that is needed from this motor to this mechanical system here is given by this expression over here. So that's the torque that needs to be, that's the force and then what is reflected onto the motor, but the electromagnetic torque or electromechanical torque that is needed from the motor is really this torque due to the load that is reflected onto it, plus the torque required to accelerate this motor itself, because this motor has some moment of inertia, J sub m. So this is required by the motor, and the sum of these two is this electromagnetic torque that is needed from, it needs to be generated by this motor. So let's go on to another mechanism, which is gears, as I mentioned, very commonly used. And here we are gearing it up. That is, we are increasing the speed of the load. That's how this drawing is put together. So we have this motor producing this electromagnetic torque, its inertia over here, and then we have this load which produces this opposing load torque and its moment of inertia. And let's assume for the time being that this is the gears are ideal. Okay, so what we need to do is to look at the radius of these two gears. This gear at the motor end has a radius r1. The gear at the load end has radius r2. Okay, and the speeds are different now. Omega m at the motor end and speed at the load end over here of the load. So you can see that r1 times omega m on the motor side has to be equal to r2 times omega l on the load side here. Okay, and you can see that power transferred across each gears, is coming from the motor end. It's omega m times T1, so this torque here, and omega L times T2 is being transferred to the load. So T2 is this torque here. So if you assume that we have an ideal gear, no loss, then omega m, which is the speed here, times this torque has to equal omega L times this torque, or T2 over here. So we can immediately see from this equation the relationship between R1 and R2 is given by omega L over omega m, and from this equation we can see that omega L over omega m is equal to T1 over T2. Okay, and what is T1? T1, which is transferred to this gear over here, this torque, is the electromagnetic torque produced by the machine minus the acceleration torque required to accelerate this motor itself. So that's T1, and T2 is equal to the opposing load torque plus the torque required to accelerate this load inertia. So that is T2, and as you can see from this equation, T1 and T2 are related by this ratio here, omega m and omega L. So you can see that you can write these equations here, and you can see that for gearing up, that means increasing the speed of the load here. We have the speed is increased. That means omega L is greater than the motor side speed, and the torque is decreased. So T2 is less than T1, and in that case, this R2 has to be less than R1. And the opposite is true, where we are trying to decrease the speed of the load. In these systems, using electric drives, not just this motor, but motor is just a part of the electric drive arrangement, we can have a four-quadrant operation. So here, this speed of the system is plotted against the electromagnetic torque. So let's say that this motor is operating in the forward direction. So we have positive speed, we are supplying positive torque, and therefore we have positive power input from the motor into the load here. Okay. So motor is running at some speed omega m, but we want to reduce this speed. So this is called regenerative braking in the forward rotational direction, forward direction. So in this case, the speed is still positive because the motor is still turning in the positive direction, but we make this electromagnetic torque produced by this electric drive to be negative, and therefore the power flow becomes negative. That means the kinetic energy associated with this system is being converted into electrical power and energy, and this power is flowing in the reverse direction. Okay, so that's why it becomes negative. Now, here, this system is motoring in the opposite direction. So in this case, as you can see, in this quadrant, the speed is negative. This is a 0 point over here. So the speed is negative, and we are applying a negative torque because we want to, the direction of this torque is negative. That means of the direction opposite to what you had over here, right? So this negative torque and negative speed would result in, again, a positive power, because power is really the multiplication of torque and speed. So the power is coming from the motor to the load. So that's why this power is positive. But if you want to do regenerative braking in this reverse direction of rotation, then what we need to do is to make this electromagnetic torque positive, while the speed is still being in the reverse direction, negative. So you can see that positive torque and negative speed would give us a negative power. That means we are doing this regenerative braking. We are taking the energy from the inertia of this system and converting it to electricity, and it's going back to the electrical system, which may be feeding this motor. And we also have to be aware of dynamic operation. We need to change perhaps the torque very quickly, and we need to make sure that we reach the steady state point without much oscillations. So we need to design our controllers using the control design rules, but also we will see that it will be a great help to model these machines and the load in a proper way, so the design of these controllers is simplified. So this brings us to the summary, where we looked at mechanical system modeling and coupling mechanisms. We talked about electrical analogy and electrical modeling. We looked at various coupling mechanisms, and we looked at four-quadrant operation, where we could do regenerative braking in the forward direction of rotation, as well as regenerative braking in the reverse direction of rotation. And we also looked at dynamic operation.